Another hello from West Virginia. Okay, so we are not in West Virginia and we are definitely going to do joke of the day. Are you ready? I know you are. So my joke of the day is, what kind of bird is sad? What kind of bird is sad? A bluebird. Well, even though the notes are in blue, they are definitely not sad. We're going to take a look at the natural base e. Now, we've been looking at exponential functions, and you see some exponential functions here. And remember, when you have an exponential function, what's going to happen is it's going to give you a very quick curve in your graph. Notice that when we graph 2 to the x power, and we put a negative 2 in the exponent, giving us a 1/4, because remember, negative in the exponent means flip. And whenever we put a negative 1 in the exponent here, again, meaning flip, we get a 1/2. Now we're into our positive exponents of 0, giving us a 1, because anything at all to the 0 power is 1. And an exponent of 1 gives us a 2, an exponent of 2 gives us a 4. And when we graph that exponential, it gives us this green graph right here. And like I said before, a very quick ascent. And that's what an exponential growth or an exponential function looks like. Very, very quick upswing. Now notice that when we do 3 to the x, similar idea here, putting in negative 2, negative 1, 0, 1, and 2 as our exponents, these negatives will indicate in those exponents to flip, and when you flip 3 to the negative 2, you get 1/9. When you flip 3 to the negative 1, you get 1/3. Once again, anything to the 0 power is definitely a 1. 3 to the first is 3, 3 to the second is 9. Notice as you compare the graph of 3 to the x to the graph of 2 to the x, with 3 to the x, the ascent is much quicker, a much sharper curve up. And that's something we talked about in the previous video about your exponential functions. We said the bigger the base, the steeper the graph. And you can see that. When we go from a 2 to a 3, that bigger base did give us, in fact, a steeper graph. Now, that review of exponential functions allows us to look at the idea of the natural base e. It is still an exponential function, as you can see right here. It's just instead of your base being numbers like 2 or 3 or what have you, the base is going to be an e. Now let's talk about where this e comes from. E is the value that when you take this, this expression, 1 plus 1 over n to the n power, when you take that expression and your n gets larger and larger and larger, so in other words, as your n approaches infinity, this value of this is going to approach this number right here, 2.718281827, and goes on forever and ever and ever. It never repeats and it never ends, which makes it what type of number? Yes, an irrational number. So e is one of those irrationals, like pi, like square root of 2, like square root of 3. So, because this number comes up a lot, and not only does it come up in this expression, it shows up in nature an awful lot. So that's why typically we call it the natural base e, because it is something that occurs naturally over and over and over again. But when you take this number right here and you make it the base of an exponential function, it will give you another graph that's going to be that sharp ascent curve. So, let's take a look at the fact that this e is between a 2 and a 3. This is why I put the graph of 2 to the x and the graph of 3 to the x on there. That e value is between a 2 and a 3. So it makes sense that since e is between 2 and 3, then this graph, this function, it is going to be between these two graphs. And take a look at how we are graphing this e to the x. Notice here, yes, it is between those two graphs. When you take your e and you raise it to the negative 2 power, what's happening is you're taking this number that is currently over a 1, and again, a negative in the exponent is going to indicate flip. So you will flip this, it'll be 1 over that number, and then you're going to square it. When you do, and you punch those numbers into the calculator, you're going to get approximately a 0.14. I'm simply rounding to the hundredths place here. But 0.14 is a little bit bigger than 1/9 because 1/9 is 0.11111111 repeating. So it's a little bit bigger than that and smaller than 0.25, which is what 1/4 is. So yes, in fact, it does sit between those two. Here, when you take e to the negative 1 power, once again, that negative indicates flip. So this is currently over a 1. When you flip it, it becomes under a 1. You're not going to square it or anything, but you're going to take a 1 and divide it by that number. You will get approximately 0.37. Again, that is rounded to the 100th. But notice that 0.37 is a little bit bigger than 1/3 because 1/3 is going to be 0.333333 repeating. So it's bigger than that, but smaller than 1/2. So once again, it sits between those two. Now, anything at all to the 0 power is 1. Notice every one of these graphs has that y-intercept of 0, 1. Also notice, when you take e to the first power, it is exactly that number right there. And again, I've rounded it to the hundredths place, 2.72, but that is between a 2 and a 3. So when you get here to x being 1, notice it does sit between this y value of 2 and this y value of 3, which is sitting right up here. It does sit between those two. And then when you get to the second power and you take this number right here and you square it, you get approximately 7.39, which is between a 4 and a 9. So here's that y value of 4, here's that y value of 9. Yes, this is sitting between. So the statement that here does make sense, that that graph is going to be between the two graphs. Also notice the similarities. We talked in the previous video about the characteristics of your exponential functions. This being an exponential function, it does carry those characteristics. Notice this is exponential growth. Growth indicated that this base here is going to be bigger than a 1, and yes, that base is bigger than 1. So we do have an increasing graph, and like we said, the bigger the base, the steeper the graph. So when this base is bigger than this base, it does give a steeper graph. We also talked about the x-intercept, that there was not going to be an x-intercept because this x-axis is an asymptote, and that occurred here with this graph. As your x value decreases, this y value is going to get closer and closer and closer and closer to 0, but it's never going to get 0. So in other words, this graph is never going to touch the x-axis, it's never going to cross the x-axis. So with that being the case, you're not going to have an x-intercept, which was one of the characteristics of your exponential functions. We also had a characteristic of your exponential function that the y-intercept was going to be a 1, and you saw that right here because remember, y-intercept means make the x 0, and in this, when you make that x 0, like we saw right here, anything to the 0 power is a 1. So it does have the same y-intercept. We also noted the domain and the range. They're going to be the same as in that previous chart. Because notice this domain being all these x's, this graph's going to continue forever in this direction, forever in this direction. So all the x's that are being covered, there's nothing that cannot be put in for your exponent. There's no restriction on what you can put in there. So your domain is still going to be negative infinity to positive infinity. And your range, we said the range previously on your exponential functions was 0 to infinity, not including 0, and that's the case here as well. 0 to infinity is still going to be your range. So you can see that those characteristics of your exponential function still hold true for your natural base of e, because when you use that e as the base, you have an exponential function there. So I hope that this helps to explain this idea of the e, and the e, like I said, it's similar to pi. Nature happened, and so the mathematicians way back then noticed that relationship of pi happening over and over and over again. And since that value of 3.14159265 that goes on forever and ever and ever, never repeats and never ends, because it showed up so much, rather than writing that out so many times, they said, let's just give it a symbol. We're going to call it a pi. This happened as well. It showed up so much that rather than having to write this out over and over and over again, they said, let's give it a symbol. We're going to call it an e. It's a similar idea. So this is a very valuable number. You'll see it show up a lot as you continue on in your math courses and your science courses, even in a lot of your financial courses. So I hope that you get that understanding of e, and I hope that helps. Have a great day.